came up with an equation that looked like so. We have the drain current is equal to mu times CMOS times W over L times VGS minus VT times VDS minus VDS squared over 2. Now, if we were to plot this equation, ID, our drain current, versus VDS for a fixed VGS number, we would see something like this. Where this would peak for a value of VDS that was equal to VGS minus VT. But we know that the curve for a transistor doesn't look like this, so what's wrong here? We know that current should never decrease with an increasing drain to source voltage, because all we're doing is increasing, or we should be increasing the lateral E field, and that should increase the velocity of the particle. So what happens is that at the end of the channel, we want to see that VGD is equal to VGS minus VDS. And at the end of the channel, near the drain, VGD becomes less than a threshold voltage. And we know that in order for the channel to be open, we need to have the gate to drain voltage being greater than that threshold voltage. So here the channel is pinched off. And current no longer depends on VDS. So if we modify this plot to a correct form, we see our plot of ID versus VDS now looks something like so. Where once VDS is equal to a VGS minus VT, the device enters saturation. So before this point, we have triode, or linear region. Of course, down at zero current, this is cut off. And here we have the device entering saturation. Now remember, saturation is good for a MOS device, bad for a bipolar device. So our condition for saturation is that VDS is greater than VGS minus VT, and that causes the channel to be pinched off at the drain. So if this is the case, we can write that our drain current in saturation is equal to 1/2 mu COX times W over L times VGS minus VT squared. We call the term VGS minus VT sometimes we call it VOV, which is the overdrive voltage. Now we can also look at a plot of our drain current. We'll look at a plot of the square root of our drain current versus VGS, And that would look very similar to the bipolar transistor case, except that we would have a linear current after VGS became greater than the threshold voltage. So this is called the saturation region for the bipolar device. Now, there are some limitations to this model, which we call the square law model for a MOS device. So as we make the devices smaller and smaller, we're seeing that the square law equations are becoming less valid. Due to short channel effects. And of course, one of the assumptions that we made is that the device does not conduct any current until the gate to source voltage reaches a threshold voltage. But in fact, below VT, current does flow. And this is a so-called subthreshold current. In fact, in a MOS device, below the threshold voltage, the current and voltage relationship is exponential, much like it is in the bipolar device. The current will be small in the subthreshold region, but it does indeed flow. For the purposes of this course, however, we will treat the square law equations as if they work very well. And in fact, for the devices that we'll be using, they do indeed work very well. Now, one other correction that we need to make to the model is that we said that the drain current doesn't change after we reach saturation. And in fact, the drain current does change as we increase VDS. And this is due to what we call channel length modulation. As we increase the drain to source voltage, we actually change the length of the channel effectively due to that lateral electric field. And the modification that we need to make to the drain current equation is we still have 1/2 mu times Cox times W over L times VGS minus VT squared, but we add this secondary term 1 plus lambda times VDS. So lambda is the channel length modulation parameter. And it's very similar to the inverse of the early voltage. So this lambda term leads to an output resistance. In the next part of the lesson, we'll look at the small signal model that results from these equations.